Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking about the concept of the mole, of Avogadro's number, of molar mass, and of atomic mass. So this is part of, I guess you could say, my series for introductory physics or introductory algebra-based physics on essentially like the gas laws and thermodynamics and so on. So let's get into this, shall we? The basic idea here, this is going to be kind of a different kind of lecture because there's sort of four topics that are all related that we're trying to basically tie together. So the gist of this is that if you look at, let's say, the periodic table, you can see all the elements listed on it, and in the periodic table you're given an atomic mass or an atomic weight. So for example, here is a portion of the periodic table, just a small portion, but a portion nonetheless. And if I were to pick one of these elements at random, maybe hydrogen for example, you see that there is a number below the symbol. So there's you have like the atomic number Z, so this is atomic number, and then you have the atomic symbol, so the 1 to 2 letter atomic symbol. Usually there is the actual name of the atom, so atom or atomic name. And then this key thing that I've circled down here, and maybe I should be a little more careful and try to get just the numbers. You've got this number down here. This is atomic weight or atomic mass, and what it's given in is essentially in Dalton's or atomic mass units, so 1.008 atomic mass units. And what the mole does for us, the mole is a sort of macroscopic quantity of whichever element we've chosen, such that we get a macroscopic amount of mass. So 1.008 atomic mass units is, I won't say immeasurably small. We have ways of measuring such small amounts even, but it's for practical purposes. You walk into like a physics 1 lab, a physics 2 lab, like a lab that's not really set up to do specialized measurements, is too small to measure that number. But in principle you could measure on like a scale something that has a mass of 5 or 2 or 0.1 grams. And so what the mole does is it's an amount of substance that's large enough to take these atomic particles and by counting many of them together get a mass that you could actually measure on a plain like laboratory scale, a triple beam balance or a digital scale. So this kind of defines for us the mole. The mole represents we could say a macroscopic amount of substance, and this amount kind of implies that what you're doing is having several of them, many atoms. To use an analogy, I have here one piece of paper, okay, and maybe I want to know what is the mass of this piece of paper, but all I have to work with is a bathroom scale. So if I take this piece of paper and I put it on the bathroom scale bathroom scale is not going to really change. Okay, but maybe I take more pieces of paper. I stack the paper like this. Maybe I get a bigger stack, like I go into the office and get like a ream of this paper. So now I have 500 sheets or 1,000 sheets or whatever, and now I put that onto my bathroom scale. Well, the bathroom scale now is going to actually measure something. Maybe it measures only a couple pounds, but if I have plus or minus, let's say, 1/10 of a pound on my bathroom scale, and I'm now measuring something that weighs 5 pounds, all told, then I suddenly have a good estimate within maybe 10%, 5%, 2% even, of how much one sheet of paper is, because I've weighed 5 pounds of it and there were 500 sheets, so I divide the 5 pounds by 500, and I get that each sheet therefore should weigh about 1/100th of a pound. Well, the same basic idea works here. We're taking a macroscopic amount of particles and then massing them, and then we're dividing by the macroscopic number. So what is that number? Well, that is where Avogadro's number comes in. So Avogadro's number, which is usually represented by the symbol N sub A, sometimes N sub O, but I prefer N sub A. Some people also use a capital L. And it has, historically, it basically kind of said this is how many, like 1 mole was 32 grams worth of oxygen, and Avogadro's number was the amount of oxygen atoms present in that one, in that 32 grams. And then eventually it changed over to carbon. So carbon is over here, oxygen is over here, carbon, oxygen. Changed to carbon. Carbon, you'll notice, is atomic mass 12 point something. We use specifically the isotope carbon-12. And so we kind of defined it to be that 1 Dalton was 1/12 of the mass of a carbon-12 atom. Okay, and so from there, you can convert Daltons into grams and come up with a number for Avogadro's number. Well, 5 years ago, they redefined Avogadro's number so that it would be an exact number. Essentially, it's not so much that they just redefined the number, it's that we've redefined how everything is measured around that number. So that number is given an exact value, and we change our scales to make it so that that value is correct. Our scales are made, in other words, with reference to that value. So that number is exactly 6.022140076 times 10 to the 23 per mole. So per mole is written as mole to the -1 power. And that is the exact value of Avogadro's number. That's how it's been redefined. Okay, so tying this stuff together, there's then another quantity called molar mass. And molar mass of a substance represents the mass of 1 mole of substance. Okay, so how is that related to this previous discussion of the periodic table? Well, again, we look at this atomic mass, 1.008 AMU. Well, it turns out that this atomic mass is very nearly equal to the molar mass. I think that with the definition of Avogadro's number to being exactly this, as opposed to its previous approximate value, 6.022140076 blah 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 times 10 to the 23, I think that the the precision, the difference between atomic mass and molar mass is usually on the scale of 1 part per like 10 billion. It's like a difference of 1 times or 2 or 3 times 10 to the minus 10 between this atomic mass and the molar mass. So therefore, if you're looking at these numbers on the periodic table, while they are truly telling you atomic masses rounded to within some number of digits, they're also actually telling you to the same number of digits the molar mass. You'd only be able to get a difference if you were to add a whole lot more digits to all these numbers. Okay, so example, periodic table says for oxygen that we have 15.999. So oxygen O, or oxygen if you prefer, has 15.999 AMU for atomic mass, average. And that is an average, by the way, because there are more than one isotope of oxygen, and so it's kind of weighted by what percentage of oxygen occurs in each of these isotopes. But in any case, this is like your average value. We can also therefore write oxygen has molar mass of 15.999 grams per mole. And so that in turn lets us get what is the mass of one oxygen atom. So one O atom, one oxygen atom, we have molar mass, and by the way, molar mass we usually represent with a capital M for what it's worth. So we have M, that's grams per mole, and if we were to divide that by N sub A, the Avogadro's number, that's atoms per mole, then we get the mass of one oxygen atom. So mass of an oxygen atom in this case is 15.999 grams per mole divided by Avogadro's number, which will maybe approximate 6.022. I guess we could just do the whole thing. It's not like I'm going to approximate it by rounding too much, but 6.02214 times 10 to the 23 atoms per mole. And so if you divide these two numbers by each other, you've got a mass per atom. That comes to 2.65669. So approximately 2.65670 times 10 to the minus 23, and the units would be grams per atom. Now, in actual fact, this is an average mass per atom. Individual atoms of oxygen, assuming that there's not any relativistic effect on them, are not going to actually have this mass, because individual atoms either are an oxygen 16 or an oxygen 14 or a 15 or a 17. They're different isotopes, and each of those isotopes does have a particular mass associated with it. So an O16 will be very nearly, though very slightly larger than this. An O14 will be somewhat less massive than this, about 1/8 less massive. in fact. Alright, well that's all that I wanted to really cover in today's short video. Hopefully this helps you understand these concepts a little better and helps with homework questions and whatnot. So I hope you learned something, and thanks for watching.